Good morning, dear students. Hope you are doing good and listening classes well. Dear students, as we are discussing the topic distribution system, we learn several topics with respect to the water supply. Here, today we are going to discuss about the topics which you must know and also you must learn the things with respect to this treatment, most particularly finding of coagulant dose, design of sedimentation tanks, and you must know the process of examining water and also the remedial methods to remove the pollutants, which are pollutants in the sense the substances which cross their limits. So far we have seen different technologies and different methods also we have seen in the supply of water. Today we'll discuss about the topic equivalent pipe method, and also if time permits we'll discuss the other topic also. See, in the previous class, that means earlier we have seen, we are already seeing the Hardy cross method, where we have seen the the equations, and we have solved. That means we learned the concept where the corrections are applied in each successive trial. That means what I'm speaking is here. The head loss in each pipe is determined by pipe flow in this Hardy cross method. What it speaks to us, the head loss in each pipe is determined by pipe flow formula. It's very easy and nothing is there in the equation. Simply you can learn it. The corrections are made the flow in each pipe until the heads are balanced. And one word, it is fully depends, or else is fully following principle of connectivity satisfied in each section. So here, let us assume that now QA is assumed flow and Q is the actual flow, and it can write as delta factor, delta equal QA, and it is approximately equal to Q, equal to in the sense a slight difference. QA is QA and Q, that is the different, definition where QA is assumed flow and Q is the actual flow. And Q is here Of course, assumed flow and Q is actual flow. Both are different, not similar. See here, different in the sense slight diversions may be existed. See here, delta is called, I mean, Q is assumed flow, QA is assumed flow, and Q is the actual flow. Now, head loss in the pipe under reference is HL, and it can be denoted with HL equal K into QA, where K is constant and depends on size of pipe. You must write, and also determined by Hazen-Williams formula, which states as per Hazen-Williams formula, which says HL equal to K into Q power 1.85. How this 1.85 come to existed? According to Hazen-Williams formula, X equal 1.85. HL equal X in the sense here that I mean equal 1.85 and HL equal K into delta plus QA. What is why this delta QA? Just have a look here. Q equal delta plus QA. Simply we are substituting. See here then. Simply we are applying binomial equations, and we can write it like this: K into Q power X plus X QA power X minus 1 into delta. For closed pipe system, the head loss is 0, and it can be written as, or else it can be written as sigma K into QA power X plus X QAX power minus 1 into delta equal 0, as it is the 0 in the closed, it is the closed pipe system. Head loss is 0, and it can be write as C here, or sigma K A X equal to, simply one more time here, minus sigma QA power X minus 1 into X into delta. Hope you understood how it comes. Simply we are just applying binomial equation. And here for closed pipe system, delta is negligible. It can take closed pipe system, delta is negligible. So we are just taking out this delta factor. See, that means here delta equaled minus sigma into K into QA power X by delta QA power X minus 1 into X. And here delta equaled sigma L minus sigma HL by QA. This is the formula as per the Hardy-Cross method. Now, how we gone, or else how we got this formula? This is the derivation part, and it is the print. Print in the sense evidential, and how we solve out this one. The next one is equivalent pipe method. See, equivalent pipe method in the sense here, this is useful in rendering a complex network of pipes into an equivalent pipe system. Here, what it is speaking to us, complex network pipes are replacing or else into an equivalent pipe system, giving the same discharge and loss of head in the complex system. Complex systems are just replacing, just converting, just making into as equivalent pipe system with same discharge and same loss of head. What we observed, what is existed in the complex system. For purpose of analysis, the entire network of pipe is considered to split, or is considered into split into two portions. One is pipes in series, pipes in parallel. Now we'll see one after one. What is pipes in series? Pipes in series, pipes carries chosen values of discharge Q1 flowing through branches AB and BD. See here, the flow is Q1, known value of discharge flowing from AB and BD. That's what mentioned here. Q1 flowing through branches AB and BD, and Q2 flowing through AC and CD. Q2 is flowing through AC and CD. Knowing the discharge, say Q1, knowing the discharge Q1 and the diameter of pipelines AB and BD through which water flows. By knowing the discharge, how much of discharge is taking place, and the diameter of pipelines through which water flows, by knowing the details, it is possible to determine the single pipe by name AD. It is possible to determine loss of each one in the total length AB plus BD. A single length of equivalent pipe AD of known diameter can be selected to give the same value of Q1 discharge and loss of head H1. Understand? See here, we are just taking this. Instead of AB and BD, we can Q, a single length of equivalent pipe AD of no diameter can be selected to give the same value of discharge and same loss of head. Simply there is a method, namograph method. With the help of namograph method, simply it is possible to determine, see here, to determine the loss of head in the total length AB plus BD. With the help of namograph, we can find out total loss of head AB and BD, and a single length of equivalent pipe from A to D can be selected with known diameter, which give the same value of discharge Q1 and loss of head H1. That's what pipes in series. Now, what is pipes in parallel? Same way, in this case, it is assumed that the loss of head through pipes in parallel, ABD and ACD, is the same. Loss of head through pipes in the parallel, ABD and ACD, both are same. If a certain loss of head is now assumed to occur in either arm length ABD or ACD, flows through the arms can be worked out and added together to see the total flow corresponding nearly to the original flow Q. The size and length of single pipeline can then be calculated to give the same discharge and loss of head. Here also what we are doing here, in this case, by using namograph, we are able to find out the loss of head of total AB plus BD. By knowing that a single length of equivalent pipe AD of known diameter can be selected to give the same value of the discharge Q1 and loss of head H1. Similarly, in the case it is assumed that ABD and ACD both are having assumed that loss of head through pipes in parallel, ABD and ACD is same. If a certain loss of head, say H1, is now assumed to occur in either ABD or length ABD and ACD, flows through the arms can be worked out and added together, we can nearly and we can add together to see the total flow nearly to the original flow Q. See here, if a certain loss of head is now assumed to occur in either ABD arm length, in either arm length ABD and ACD, flows through the arms can be worked out and added together, to see the total flow which is corresponding nearly to the original flow, where the size and length of single pipeline can be calculated to give the same discharge and loss of head. Understand? This is about pipes in parallel. In this case, we have seen AB and BD. The known volume of discharge is Q1. With the help of namograph, we can find out the head loss. By knowing the values, we can select, or else we can a single length of equivalent pipe AD with known diameter can be selected to give the same value of the discharge Q1 and loss of head H1. This is pipes in series, whereas the similar thing parallel, but a difference in process. ABD and ACD is same, the known loss of head is same. By knowing and assuming H1 head loss, and that can be worked out, added together these two to see the flow corresponding nearly to Q. With that, the size and length of single pipeline can then be calculated to give the same discharge and loss of it. This is about pipes in parallel. Pipes in series, we have seen equivalent pipe method. In the hardy cross method we have seen, and we have seen the pipes in parallel method. The next one is pressure in the distribution system. Pressure in the distribution system. What is the pressure in the distribution system and what is exactly happening? See, have a look over there. When the water is being supplied, there should be a sufficient pressure to meet the consumer requirements, but it is lost, and it may last due to the friction in pipes, entrance of reducers, valves, bends, meters, etc. Why the sufficient pressure is not unable to maintain in the distribution system? Because to meet the consumer requirement, why we are unable to produce, we are unable to see here when the water is being supplied, there should be a sufficient pressure to meet the consumer requirements, but it is less because of what? Due to friction in pipes, due to walls, bends, and even sometimes meters. If a pipeline is straight, if the supply pipeline is straight, obviously the water flow will be very fast and very quick. If the same pipeline has number of bends, obviously the time will be prolonged for the same flow of water. See, from point X to Y, if the pipe is single pipeline, obviously the flow will be very quick. The same pipeline having number of bends, the flow will be differ when compared with the flow in the straight pipeline. That's what I mentioned here. When the water is being supplied, there should be a sufficient pressure to meet the consumer requirements, but it is lost due to friction in pipes, entrance of reducers, valves, bends, meters, etc. There should be a sufficient head, pressure and the sufficient head in the pipes connected to the buildings by considering the height up to which the water should raise to meet the requirement of different story of the building in that location. See, what is it speaking? There should be a sufficient head in the pipelines with respect to the height of the building. With respect to the height of the building up to which the water has to reach, and requirements of different story of the building in that location. The third one is the pressure which is required. And see, I said that in the second point, there should be a sufficient head in the pipes connected to the building by considering the height up to which the water should raise to meet the requirements of different story of the building in that locations. Normally, the pressure which is required to be maintained in the distribution system is as follows. Understand what it is here? The first point we have seen that sufficient pressure has to be maintained, but it is losing because of the friction in the pipes, that is friction in pipes, entrance of reducers, valves, bends, meters, etc. See here, walls, we have seen different types of walls, and meters also we have seen. While as the water is entering from inlet to and passing out through outlet, automatically the flow will be calculated. We have seen in one type of meters, in the previous class, that means displacement type of meters. The same way, the sufficient head has to be maintained. See, if the water is not maintaining, if the water sufficient head is not maintaining the pressure, sufficient head is not maintaining the pipelines, supplying water to high-rise buildings is somewhat difficult. That means sufficient has difficult in the sense for better flow, for good supply, there should be a sufficient head in the pipes, especially, whenever the water is supplying, sufficient head has to be maintained. See here, and it should be in the point, sufficient bed in the pipes connect to the buildings by considering a height up to which water should raise to meet the requirements of different story of the building in that location. Normally, what are all the different precautions? What are all the different, conditions which we need to maintain, which we need to consider is the pressure which is required to be maintained in the distribution system depends on the following factors. See, what is the point? Next point, the pressure which is required to be maintained in the pipelines or else in the distribution system depends on the following factor. See, understand what are all those factors? We'll see one after one. We'll see one after one. We'll see one after one, hopefully in next class. Today, we have finished and about the pressure, pressure in the distribution system, small introduction. and pipes in parallel, pipes in series of equivalent pipe method. And one more time we discussed about is RD class. If any doubts, please contact me either phone, message or mail. Thank you.